In this video, we will find Fourier transforms for some functions. So first, let us start with Fourier transform for radio frequency pulse. Start with Fourier transform radio frequency pulse. So this is how a radio frequency pulse will look like. Right, this is my time axis, and this is my radio frequency pulse x of t. This is a cos function. So this is my origin. This is my negative tau by 2, and this is my positive tau by 2. My amplitude is 1, and on the negative side it is minus 1. So this is the radio frequency pulse. The width of the pulse is tau. The width of the pulse is tau. So for this, I have to find the Fourier transform. So how can I write this function? I can write this function as a product of two functions. What are those two functions? That is, one is a cos function that extends to minus infinity to plus infinity. Right? This is a cos function. Cos omega naught t. I'll just call it cos omega naught t, and I'll multiply it with another function such that my resultant function lies only in the interval minus tau by 2 to plus tau by 2. Outside this interval, the x of t must be equal to 0. So to obtain x of t from cos omega naught t, what we should do, we should multiply it with a rectangular function that extends from minus tau by 2 to plus tau by 2. Now this is my rectangular function with amplitude a. So this I will call it as pi t by tau. Right? So if I multiply these two functions, the first function is extending from minus infinity to infinity. The second function is from minus tau by 2 to plus tau by 2. So from minus infinity to minus tau by 2, the first function has some value, but the second function, the value is 0 in this range. So if I multiply the two, anything multiplied by 0 is 0. So my x of t is 0 in the range minus infinite to minus tau by 2. Same thing for tau by 2 to infinity. Only in the range of minus tau by 2 to plus tau by 2, I am multiplying cos omega naught t with 1. That is how I'll get just cos omega naught t in this region. So now let me write x of t is nothing but my rectangular function into cos omega naught t. Rectangular function, that is pi t by the width of the pulses tau into cos omega naught t. Now what is this equal to? Now I have to find the Fourier transform of this function. So let me just simplify this function further. In place of cos omega naught t, I can write it in terms of e power theta plus e power minus theta, e power j theta plus e power minus j theta by 2. So let me simplify it. Pi t by tau into e power j omega naught t plus e power minus j omega naught t divided by 2, right? I will separate the terms. So pi t by tau into, here I have a constant of 1 by 2 into e power j omega naught t plus again the constant 1 by 2 pi t by tau into e power minus j omega naught t Now let me look at what is the Fourier transform. Now if I take Fourier transform on the left side, I can take the Fourier transform on the right side also, right? Fourier transform of this plus Fourier transform of the second term. Now let me look at what is the Fourier transform of pi t by t. Pi of t by tau. What is the Fourier transform? Fourier transform is a tau sampling omega tau by 2, right? My a is equals to 1, so it is tau sampling omega tau by 2. Now I need a shifted version of pi t by tau, the rectangular function, and its shifted version, right? Sorry, not shifted version, sorry. It is according to this thing, my time signal has a phase shift, right? This is the Fourier transform of rectangular function. Now according to frequency shifting property, pi of t by tau into e power plus j omega naught t will have the Fourier transform. What will be the Fourier transform? It is nothing but a shifted version of tau. Sorry, it's a shifted version of this Fourier transform, that is tau sampling omega minus omega naught into t, omega minus omega naught into t. Instead, that is not t, it is tau. Right? Now instead of plus, if I have a negative sign here, I'll have a positive sign here, right? Now I will substitute this Fourier transform in place of these two terms on my right hand side. Let me substitute that. So that is equals to 1 by 2 tau tau sampling of omega minus omega naught into tau by 2 plus tau sampling of omega plus omega naught into tau by 2. Now tau is common, so what can I do? I can take tau common from both terms. So this will be my tau. So this is my final answer. Tau by 2 sampling of omega minus omega naught into tau by 2 plus sampling of omega plus omega naught into tau by 2. So this is how we can find the Fourier transform for the given function. Now let us find the Fourier transform for a triangular RF pulse. Triangular RF pulse. So let me draw the triangular RF pulse first. My triangular RF pulse looks something like this. So my pulse will lie in between these triangular RF pulse. So it's a cosine. Again, this is from minus tau by 2 to tau by 2. Minus tau by 2 to tau by 2. For this, we need to find the Fourier transform of x of t. Let us say this is x of t. Now x of t I will write as product of two functions. The first one is a cos function. First one is a cos function. Cos omega naught t. And the second one is a triangular function. Second one is a triangular function extending from minus tau by 2 to plus tau by 2. This is a triangular function represented by a triangle of t and width tau, right? This is how we represent a triangular function. Now we have to find the we have to find the Fourier transform of this, Fourier transform for this function, and then find the final Fourier transform for this function. So first let us find Fourier transform of triangular function t by tau. So now I can represent my triangular function. How can I represent my triangular function? Let me just represent in two different ranges, from minus tau by 2 less than t less than 0, 0 less than t less than tau by 2, right? That is how I can represent my triangular function. Now the amplitude here is 1, so I have to find the line equation for this part of the signal from minus tau by 2 to 0. So what is my line equation? My line equation is going to be, if you calculate it, it will come to be 1 plus 2t by tau, 1 plus 2t by tau, and the second one is going to be 1 minus 2t by tau, right? Now I can find the Fourier transform of this second function here using the traditional analysis equation, that is minus infinite to infinite x of t e power minus j omega t dt. Instead of finding that way, I will find using a property of Fourier transform. So let me just consider this function here. I'll just write it here, right? I'll consider my function from this part till this part. Right, this is my x of t, or let me say triangle of t by tau, from minus tau by 2 to plus tau by 2. Now let me differentiate this term here. Let me differentiate it. So if I differentiate the signal, what will I get? So here it is 0, so differentiation of 0 is 0, and here also it is 0, so differentiation of 0 is 0. So outside minus tau by 2 and tau by 2, outside this range, my signal is going to be 0, right? In the range minus tau by 2 to 0, what will my signal look like? It is 1 plus 2t by tau. Now I have to differentiate with respect to t, right? I have to differentiate. So differentiate the first equation here, 1 plus 2t by tau with respect to t, d by dt of 1 plus 2t by tau. Differentiation of 1 is 0, and differentiation of 2t by tau with respect to t is 2 by tau. So in this range, the value of this signal is 2 by tau, right? It's a constant. In this range. Then what happens in this range here? In this range, I have to differentiate. In the range 0 to tau by 2, I have to differentiate 1 minus 2t by tau with respect to t. So the value is going to be minus 2 by tau, right? So let me write it clearly. Here it's going to be minus 2 by tau, and the range, the x-axis is going to be plus 2 by tau, right? This is my differentiated version, that is d by dt of d by dt of d by dt of triangular function d by tau. Now I will differentiate it once again. Right? Let me differentiate it once again. Once again. What is the differentiation of this? Is what now? This is looking like a unit step. It has a step here. So if I differentiate this, at minus tau by 2, since there is a rising edge at minus tau by 2, the edge is rising from 0 to some value t to t 2 by tau. It is increasing. So if I differentiate this, I'll get a impulse in a positive direction since it's a rising edge. The amplitude is going to be 2 by tau. Amplitude is 2 by tau. And similarly, at 0 from 2 by tau, it is going down to minus 2 by tau. So the total strength is going to be twice the 2 by tau, right? This is the amplitude is 2 by tau and the amplitude is again 2 by tau. So it is 4 by tau. So here I have a impulse which goes in the negative direction. Impulse that goes in the negative direction, right? Minus 4 by tau. Why negative direction? Because my signal is changing from plus 2 by tau to minus 2 by tau. It is going down. So I have a negative impulse here. Again at tau by 2, what is happening? At t is equal to tau by 2, from minus 2 by tau to 0, my signal is increasing in the positive direction. So my impulse is again in the positive direction. What is the strength of the impulse? This much, right? Whatever is here, that is 2 by tau. 2 by tau. So this is d square by dt square of the triangular function, right? D square by dt square. Now let me find the Fourier transform for this function, Fourier transform for that function. So first, how can I write this function? I can write it as d square by dt square, d square by dt square of the triangular function is equals to, what is it equals to? It is equal to sum of three impulses, right? There are three impulses in this function. So it is equals to 2 by tau, 2 by tau del of, where is the first impulse? Where is the first impulse? First impulse is at minus tau by 2 del of t plus tau by 2 plus del of another impulse is at tau by 2, so t minus tau by 2 plus 1 by tau, sorry, not plus, and we have a third impulse at origin and its strength is minus 4 by tau. minus 4 by tau del of t. Right? This is the equation, right? Now I will take the Fourier transform on both sides. So Fourier transform on both sides and Fourier transform on both sides. Now, according to differentiation property, time differentiation, right? We are differentiating in time. According to differentiation property, what do we have from differentiation property? D by dt of f of t, d by dt of f of t has the Fourier transform, j omega, it has the Fourier transform j omega into f of omega. If you prove this for multiple differentiations, it will look like this. D power n by dt power n into f of t will have the Fourier transform j omega whole power n into f of omega. So here n is equals to 2. So let me just substitute n is equals to 2 in this part. So what will happen? J omega square into f of omega into f of omega, j omega square into f of omega, that is equals to, on the right hand side we have impulse functions. We have 3 impulse functions. So for that I'll take the Fourier transform 2 by tau Fourier transform of delta of t. What is Fourier transform of delta of t? Delta of t is 1, right? Now delta of t minus t naught, what is the Fourier transform? It is e power minus j omega t naught, right? So in place of t naught I have negative tau by 2. So it is e power j omega naught tau by 2 plus e power minus j omega naught tau by 2 plus minus 4 by tau delta of t, the Fourier transform is 1. Now e power j theta plus e power minus j theta is nothing but 2 cos theta. So instead of that I can write 2 by tau into 2 cos theta, that is 4 by tau cos omega naught tau by 2, right? 4 by tau cos omega naught, omega naught, is it omega naught? Sorry, it's just omega, my mistake, it is just omega. Omega tau by 2 minus 4 by tau. So if I take 4 by tau common, it is something like this, right? Now this can be further simplified. Then on the left hand side I have f of omega into this reduces to minus omega square. So that minus omega square I'll get it to the right hand side, right? Minus omega square I'll get it to the right hand side. So I will divide by omega square here, and negative sign I'll multiply inside. So I am left with something like this. Okay, negative sign I'll just put it inside. So 1 minus cos of omega tau by 2 This is equal to 4 by omega square tau into 2 sine square omega tau by 2, right? Now if I simplify this, 4 into 2 becomes 8. 4 into 2 becomes 8. So 8 by omega square tau sine square omega square by 4. And this is 4. Now that is equal to, now I'll multiply and divide by, so let me just convert this first. 8 by omega square tau into sine omega by omega tau by 4 whole square. Now I'll multiply and divide by omega tau by 2 whole square, right? I'll multiply and divide by omega tau by 4 whole square. Same thing here, omega tau by 4 whole square. Then simplifying this, I will get omega square and omega square gets cancelled. Tau, here there is tau square and here there is tau, so I am left with a tau there, and here I have 8 and here in the denominator I have 16, so I am left with tau by 2. So tau by 2, and this is nothing but sampling of omega tau by 4, omega tau by 4, and I have a square of the sine term, right? So sampling square of omega tau by 4. So far what I have done, I have just found the Fourier transform for the second function here, right? This function. Now I have to find the Fourier transform for the triangular RF pulse. So let me erase some stuff. Now I'll find for the x of tau. Now x of tau is product of these two functions. So what can I write? Instead of cos omega naught t, I can write e power j omega naught t by, sorry, e power j omega naught t plus e power minus j omega naught t by 2. So my x of omega is equals to Fourier transform of, right? Fourier transform of the triangular function. Here I'll just represent triangular function with a triangular function, and cos omega naught t place I'll write e power j omega t plus e power minus j omega naught t by 2. So I will separate the Fourier transform here, j omega naught t by 2 plus Fourier transform of a triangular function into e power minus j omega naught t divided by 2, right? This 1 by 2 and here 1 by 2 is a constant, so I can get it outside, right? Instead of writing here, I can just write 1 by 2 outside. I can write 1 by 2 here and 1 by 2 here. Now that is equal to 1 by 2. I know the Fourier transform of the triangular function. This is my Fourier transform for the triangular function. Now there is a phase shift in the time domain. So what does that represent? That represents corresponding frequency shift. Right? So what will be my Fourier transform? By using which property here? We are going to use frequency. We are going to use frequency shifting property. According to frequency shifting property, the Fourier transform of this is going to be tau by 2 sampling square of in place of omega I have omega minus omega naught into t by 4 plus again I have 1 by 2, so 1 by 2 is a common thing now, and again I have tau by 2 sampling square of omega minus omega naught, sorry, plus omega naught here because there is a negative sign here, into t by 4. Sorry, this is not t here, right? It's going to be tau. This is tau because there is tau here in my Fourier transform. This is tau. Right? So this is how I'll find it. This is how I'm going to find the Fourier transform for a triangular RF pulse. Now I can take tau by 2 common from both the terms, and I can multiply it 1 by 2, so I can get tau by 4 common, and I'm left with two sampling square functions inside. So that is how I can simplify, right? So that is how we can find the Fourier transform for a triangular pulse. Then cos omega ct into u of t. We need to find the Fourier transform for this function. So let us find the Fourier transform. Instead of cos omega ct, I can write e power j omega ct plus e power minus j omega ct divided by e power j omega ct plus e power minus j omega ct divided by 2 into u of t. Now I will separate the terms. 1 by 2 is a common term, right? And I have e power j omega ct into u of t plus e power minus j omega ct into u of t. Now I have to take the Fourier transform for this signal here. So I'll do the same thing. I'll take the Fourier transform for this signal. So what can I do? I can separate the Fourier transforms, or let me just do this Fourier transform of this whole thing, right? What is my Fourier transform of u of t? Fourier transform of u of t is equals to 1 by j omega plus pi delta of omega, right? 1 by j omega plus pi delta of omega. Now, okay, this is the Fourier transform. I should not write equal to, I should write a double-headed arrow. Now, now if I shift the frequency here by omega naught, What will my time signal be? It's going to be u of t e power j omega naught t as the Fourier transform 1 by j. It is 1 by j. In place of omega, I have omega minus omega naught plus pi into delta of omega minus omega naught. So I can write the Fourier transform as 1 by 2 is my constant, and in the Fourier transform for e power j omega ct into u of t is going to be 1 by j into omega minus omega c plus pi into what is there, delta of omega minus omega c, plus for this one the Fourier transform is going to be 1 by j into omega plus omega c plus pi into delta of omega plus omega c. Right, now I can combine these two signals here. I can combine these two signals here, take an LCM. What will happen? 1 by j omega minus j omega c plus 1 by j omega plus j omega c. So in the denominator, what will I have? I'll have j omega minus j omega c into j omega plus j omega c. That is nothing but j omega whole square minus j omega c whole square. Right, and in the numerator I have j omega plus j omega c minus, sorry, it's going to be plus j omega minus j omega c. So these two terms get cancelled and I have 2 j omega. So I have 2 j omega divided by, it's going to be omega c square minus omega square, right, plus 2, sorry, plus, there's no 2 here, plus my impulse functions. That's going to be pi delta of omega minus omega c plus pi delta of omega minus or plus omega c. The whole thing multiplied by 1 by 2. So this is my final answer.